So welcome everybody to the webinar today. We've got a special guest with us today, David Addison from Thermal Chemistry Limited, who's a local guy here from the Waikato, but travels the world these days looking at all sorts of things, and in particular a specialist in industrial boiler water treatment and chemistry. And so we're privileged to have him with us today to talk about some fairly unique and very important topics in regards to not just the performance and efficiency of your boiler plant, but also in terms of its reliability and longevity. So on that note, I'll hand the time over to David, and just a reminder for any of you that have questions through the day, today's webinar, you feel free to use the question portal, and we'll hopefully address them either at the end of the webinar or as we go through if it's appropriate. So on that note, welcome David, great to have you here, and we'll let you get underway.
Cool, all right, thanks James. All right, so what we got here is industrial boiler water treatment and chemistry, and it's a very brief introduction. My background is primarily in large fossil plants. I turned up at the Huntly Power Station as a recent graduate, expecting to be there for a summer job quite a few years ago, and it took me about 11 years to escape, so I've been kicking around boilers for quite a while, but deal a lot with cogen plants, smaller industrial boilers, all the way from little wee ones up to what we call supercritical units for large-scale fossil plants. So this is going to be let me just get this thing to work. All right, so what we're going to run through is a bit of an introduction, a bit of a what is cycle chemistry, talk about water tube and fire tube boilers, which are the most common industrial types, a little bit on what is corrosion, what is deposition, chemistry guidelines. There's a number of guidelines that you can operate plants to, and it's always recommended that you run to a guideline. A little bit about IAPS, which is the International Association for the Properties of Water and Steam, which is a free resource for cycle chemistry related information. And then we'll run through each of the key aspects of industrial boiler, cycle chemistry control, just briefly touch on each of those, and then a summary. This is a very brief introduction to the subject, and it is very complex and multifaceted. Every plant is unique to some degree, and every plant's chemistry program is customizable to a degree. It might be that you run all the time, it might be that you run once a week, it might be that you have to produce steam that has a certain chemistry because you're contacting food or you're going through a certain type of turbine. And there's a variety of advice out there available in industry. Not all of it is as correct or as correct as it should be. There's a lot of people selling various chemical treatments for industrial boilers and power boilers as well. If you think about it, you may have a vested interest in promoting a certain type of chemistry if you're going to make a bunch of money out of someone buying a certain product. The work that I do, I'm a pure consultant. We don't sell anything, don't sell any hardware, don't sell any chemicals. So we try to offer impartial advice to solve problems for people. The other thing is, this is only an hour. Further reading will be required for a deep understanding, and we're not really going to go into any great detail around corrosion mechanisms. And what we intend to do is do a following webinar some point in the next few months, where what we'll do is we'll go through sort of the key corrosion failure type problems that can occur in industrial plants and talk about what they are, how to identify them, what the mechanism is, and what the root cause is, so that perhaps in your own plants you can maybe take some preemptive steps to stop those types of problems from happening. So first up, what is cycle chemistry? It's the chemical treatment of water and steam within a boiler or steam raising plant, and it encompasses the water treatment, the makeup water. You've got to put water into that boiler somehow, so you've got to normally do some kind of treatment to that. It's the chemical treatment of the feed water and the boiler water. These two things are normally addressed separately, and then also the sampling and analysis for control. You can't control what you can't measure, so one way or the other you need to know what's going on. And this could be a fire tube or a water tube, or what we call a heat recovery steam generator system. So we'll talk about basically what those are soon. And you might have a boiler that produces what we call saturated steam, so it's at saturation temperature, or it's perhaps superheated where additional heat input's been added. And there's different requirements and different problems that occur from that. And basically all the industrial boiler cycle chemistry information and knowledge and guidance out there is derived from the science behind the power boilers and the heat recovery steam generator cycle chemistry. So a heat recovery steam generator is what we put behind large gas turbines. If you're driving on the motorway in Auckland, you go past the Otahuhu power station, that's what that is, and that's just another type of boiler, but we don't really go into too much on that. So why cycle chemistry? What we're trying to do is prevent corrosion and deposition related failures, and obviously if your boiler springs a big leak, it's not going to run, so we call that a forced outage of the feed system, the boiler, HRSG, and the steam path. So all these images here are bad days in the office. This is a severe pitting damage, which has actually caused a leak in a superheater. Here's what we call a short-term overheating failure in another plant, and this is a multicolored turbine because some of the chemical components in the feed water have ended up on a turbine, and it's not really great because it significantly impacts on the performance of a steam turbine. So what's the most common industrial boiler? It's what we call the Foster-Wheeler D-type. It's called the D-type because when you look at it in the side profile, the shape of the drum and the tubes makes a D. But basically you have a cavity, there'll be a flame going in, that might be gas or oil, series of tubes that pick up the heat. We have a steam drum up here that does the steam water separation, and there'll be a superheater on the back here if it has one of those. And that's really the most common type worldwide. And you know, this is one that's all fully clad and in service in a plant, and they range in size, but you know, from a few tons an hour to tens of tons an hour. And this is what they look like inside profile, really. It's you have a feed water drum at the bottom, the water comes in, rises, the heat there starts to boil in these tubes, comes up into the steam drum where water steam separation occurs. Steam will come out, goes through the superheater, and out it goes, and there may be an economizer tucked onto the back here as well. It just depends on the plant design. But we call that a water tube boiler. The water is in the tubes and the fire or the heat is in the gas space around that. The second most common type, particularly in New Zealand, Fonterra has a lot of these, are what we call water tube boilers, and this is basically directly evolved from the old steam trains. And here we have basically a tank which is full of water with a sequence of tubes running through it, and the fire is within the tubes. Okay, so there's a burner at one end, and the hot gases flows through those tubes, and the heat transfer occurs, and then it boils within this vessel, and then there's some steam separation, and off it goes. So water tube boilers really only produce, or in my experience, only produce saturated steam, where fire tube, sorry, I put water tube boiler on here when I meant to put fire tube, so there's a typo on that slide, so that's terrible of me. But a water tube boiler will normally produce superheated steam, where a fire tube boiler is normally only saturated steam. So it's correct on this slide, which is one, also looking at one on the outside, and here we have the burner and the end box here, and then there'll be a sequence of tubes that flames flow through there. And this slide here just really shows the difference. So we have a water tube boiler where there's the flame here, and then the water comes in as water at the bottom here, and as it rises up, it starts to form steam, and then there's a fraction of steam that comes out, and often the water gets recycled back down to downcomer. And then we have a fire tube boiler where the water is within the tank that's surrounding the tubes, and the flame or the heat flows through there. Okay, so chemistry problems are different but similar in a lot of respects. So water tube, saturated or superheated steam, and these can be low pressure, few bar, 10 bar to up to 180 bar, and that's about the limit for what we call subcritical boilers. Anything higher than that, we're pretty much getting into supercritical, which is far beyond the realms of industrial boilers, but it's very, very interesting chemistry. If there's superheated steam, and then we have to be very concerned about superheater corrosion and deposition control, because that's absolutely critical. So pretty much most industrial boilers that have superheaters will end up having some problem at some point in their lives. And the record that I've seen complete destruction of superheaters after a few years operation, I've seen complete destruction after 18 months, and I've seen complete destruction after about 5 days, but that's when they got absolutely everything wrong. Fire tube, saturated steam only, very normally only around 10 bar pressure, and less complex than water tube boilers. They're much simpler to operate. So what is corrosion? Corrosion is the wearing away of metals due to a chemical reaction. So you build your plant out of normally carbon steel is the most common material, and corrosion is that carbon steel wanting to turn back into a fall back down the energy tree and go back into the raw material that it was in the ground before it got dug out and refined and turned into a steel. So it's the disintegration of the material into its constituent atoms due to chemical reactions with surroundings, and it's basically an electrochemical oxidation process, okay? And obviously if your tube is trying to turn back into something else, eventually it'll start to leak, or you have a failure, especially if it's holding some kind of pressure. So what is deposition? Deposition is the transport of material onto a surface. So in a boiler, it's normally either a suspended solid, which has been picked up from one location. So in the case of boilers, often this is you have corrosion in one location. So you have corrosion of carbon steel. You end up with an iron oxide, probably magnetite or hematite, and then that gets transported and deposited onto another surface where that may cause you some more problems. It might be heat transfer, or it may become a location where other corrosion can occur. The other part of deposition is that if you have something dissolved into the water, like in this image here showing silica deposition inside a boiler. So what's happened is there's been a bit too much dissolved silica in there, and as the temperatures have moved around, it's changed the solubility profile, and you've had silica precipitation onto that surface. It's a problem in boilers because it affects heat transfer and it can cause overheating, and it's a major problem in steam turbines because it'll cause normally efficiency or output issues, because you get a build up onto the blades, it disrupts the laminar flow on the turbine of the steam, and then the turbine efficiency falls right away. But we don't want it. In terms of the plant itself, it's the bulk of the plant's carbon steel, already mentioned that, and what good chemistry does is it actually forms a stable oxide, a bit like your aluminium and your aluminium oxide on your aluminium beer cans. Okay, and what we're trying to form is a stable magnetite and hematite oxide on the surface, and what the corrosion does is it disrupts those protective oxides. So within any kind of boiler plant, we have protective oxides, which we get the reaction to go right. Is a very quick, very self-limiting reaction where you get a few microns of oxide formed, and it's in situ growing and it stays there. Corrosion disrupts that, or heavy deposition will deposit more material on top of that and then result in more problems. So that's basically what corrosion is. It's just disruption of those oxides. Material gets lost from underneath the oxide, and then you'll get thinning and failures. And the type and location of that corrosion depends on the design, the temperatures, the pressures, and we'll talk about that in the follow-up webinar that we'll do later on in the year. In terms of deposition, the biggest issue in industrial boilers is you get deposits on the heat transfer surfaces, so these can be the boiler tubes and the superheating tubes, and obviously things like silica, heavy silica deposits, or calcium, magnesium type deposits have quite significant insulating effects, and what that means is that the tube is no longer being cooled by the water or the steam that's flowing through it, and what happens is basically the material will approach the gas side temperature, and you'll get what we call a creep failure, and this can happen quite quickly, particularly if the tube is blocked by the deposit or some maintenance debris. But creep failures predominantly in superheaters, but they can happen in actual boiler tubes, and it's not a good day in the office, because normally if one tube goes, you've got a bunch of them that are going to go as well. All right, so history of cycle chemistry, where's it all come from? It originally came from steam trains, and this is a steam train with a fire tube boiler. Okay, you can see the tubes here, and he's having a bit of a bad day in the office because he's obviously had a catastrophic failure of his boiler. So that's where basically boiler chemistry came out of. There was the Industrial Revolution started, boilers were invented, and they started running them, and they started to have all kinds of problems of boilers exploding and killing people, and making steam trains not run on time, and the whole area of boiler cycle chemistry science was developed to try to improve the reliability of these engines, and then stationary engines in factories, and that's where it's all kind of come from. So if you need some guidance, there are some guidelines out there for boilers. ASME in the US has a guideline that you can purchase. It's the consensus document on operating practices at maybe a couple of $100 New Zealand for that. The BSI, the British Standards, have another one, recommendations for water treatment for steam boilers and water heaters. This is quite old and quite out of date. You can purchase that as well. For ASNZ standards, there's really nothing available. And then there's also these IAPS guidelines from the International Association for Properties of Water and Steam. These are free. These are primarily focused on power plants, but they do have direct applicability to industrial boilers, and there is some discussion around whether IAPS should produce an industrial boiler guideline as well. So just quickly on that, IAPS, if you've ever used a steam table, you would have used some IAPS technology. So it's a non-profit association made up of national organisations. New Zealand's a member. I'm heavily involved in it, and all very interested in the thermophysical properties of water and steam, particularly for thermal power plants and industrial applications. And you go to their website and you can find a bunch of guidelines that we'll talk about. There's ones for measuring a thing called carryover. There's volatile treatments for the steam water circuits of fossil and combined cycle plants, phosphate and caustic treatments for combined cycle and fossil power plants. There's some instrumentation guideline. There's some steam purity if you've got a steam turbine. You want to know a bit more about steam purity for your turbine operation, there's stuff there. And there's another one for corrosion product sampling analysis, which is quite useful as well. And you can get all of these off the IAPS website. If you go to the iaps.org and then click on technical guidance documents, it'll take you through to that, and they're all free and available to download. So what are the key aspects of industrial boiler cycle chemistry control? Obviously, effective makeup water treatment, we'll come to that. We're going to go through each of these. Feedwater pH corrosion control, feedwater dissolved gases control, boiler pH and corrosion control, boiler scale control, boiler blowdown control, saturated steam deposition and corrosion control, superheated steam deposition and corrosion control, steam turbine deposition and corrosion control. If you have a steam turbine, not all plants do. Condensate return purity control, sampling and analysis, layup and storage protection. That's basically what we're gonna touch on today as we go through. So first one, effective makeup water treatment. So water treatment is the removal of unwanted suspended and dissolved ions prior to entering a boiler. So if we took the lovely Waikato river water and we put that straight into a boiler, it's got both suspended material, maybe the odd swimmer and things like that still in there, and a whole lot of dissolved material. And as we start to heat that up, we change the solubilities, and we'll get an awful lot of deposition, and the water may actually be quite corrosive as well. The higher the pressure of the boiler, the more critical the water treatment is. And this is because as you increase the pressure, operating pressure of a boiler, your tolerance, I guess, for cycle chemistry problems goes down and down and down. Partly that's higher the temperature, the faster the reaction rates. Solubilities change with pressure and temperature as well. So normally, less than 10 bar boilers or around 10 bar, you want potable water. Potable water's had most of the suspended solids removed. You should have, probably less than 0.3 NTUs of turbidity in there. And normally it'll go through a water softener. And what a water softener does is it removes the metal cations only. So it takes out magnesium and calcium and substitutes those with sodium ions. And that's commonly for, say, a fire tube boiler at like a Fonterra plant, or maybe at a small industrial plant. That is commonly the only treatment in use. And that kind of works and kind of doesn't. If you're operating at more than kind of 10 bar plus, really, my recommendation is you really need to consider what we call a demineralizer. And this removes basically all of the dissolved ions. If you're taking raw water, often that plant will have some kind of pre-treatment plant on there, remove all the suspended material, and then it will go through and take out all the dissolved ions. So basically, the better the dissolved ion removal, the better the boiler makeup water in terms of quality, and because of that, you'll get lower blowdown out of your boilers. It will lower your treatment chemical demands, and it lowers your operating costs. So it's one of these things that you spend a bit more capex up front, and you build a plant that's got a good water treatment plant. Your OPEX, your operating expenses, will go down because you don't have to deal with the problem in the boiler. You take the problem away before it goes in. In water treatment plants, like I talked, the most basic is a softener, normally after potable water, or you could have an ion exchange plant where you use cation resin bed followed by an anion resin bed. So cation takes out all the positive charged ions, anion removes the negative charged ions, or you can have a cation and an anion, and then a mixed bed, which improves the performance even more. You could use reverse osmosis membranes, or you could use reverse osmosis and a continuous electrical deionization unit. 101 different ways to skin the cat on that. But basically, at a water treatment plant, these are sort of the things that we want to see for anything over about 10 bar. We want to see water out of the plant, conductivity less than 0.1 microsiemen per centimeter, what we call conductivity after cation exchange less than 0.1, and silica less than 10 ppb. And that will pretty much give you suitable quality water to avoid a whole lot of problems. But we don't just need quality, we also need the right quantity. If your plant demand is, say, 5 tons an hour of makeup water because you're using some in your process, building a 3 ton an hour water treatment plant, you're probably going to have quite a few operational problems. So the industry rule of thumb that we use when designing water treatment plants is normally 20% over what you think your maximum demand is, and you should be about right. And the problem with poor quality makeup water is it's a cumulative problem. So, I say to many people, it's, you build your new boiler, we can fill it up with whatever water you want. The failure won't happen instantly, it'll happen over time. And the further you deviate from optimum water quality, the shorter that time to failure will be. But normally we find that plants that are suboptimal in design, a few years down the track, the problems start to happen. So that's just something to think about. Water treatment is a long-term problem. And normally, when we add in water into the plant, it'll go into the condenser hot well or gets made up into the deaerator. So there'll be a point in your plant where water comes back in to replace water that's lost. So it might be lost because of boiler blowdown, it could be lost due to leakage in the plant, or it could be that you produce 10 tons an hour of steam, and in your industrial process, 5 tons an hour of that steam is consumed. It could be via some kind of air heater or direct injection into the process. So you got to replace that fluid that's lost from the system. So it'll have to come back into your plant somewhere along the line. So the next one is feedwater pH corrosion control, and the simplest way that I can kind of describe this is we have carbon steel, and carbon steel has a corrosion rate, so relative attack here, that depends on the pH. We've got the pH range of 1 to 14. So if we're operating at a pH of, say, 1.5 to 2, corrosion rate's very high for carbon steel. And as we increase this pH, that corrosion rate really comes down. Okay, and we actually get down to a minimum here. It's about 9.8 to 10 is about the minimum for what we call the ferrous ion solubility for carbon steel. It's basically wants to be at that pH, and then as we go over that pH, if we go up into the high alkaline states, the corrosion rate starts to increase again. So in most boilers and power plants, we're trying to get a pH that's alkaline, normally 8, 9, 10 in the feed water, and same for the boiler because that's optimum for the materials. Now, whether you can obtain that pH depends on your plant design and what your steam and things like that are being used for, or whether there's hot water being extracted from the boiler for another process. It may impact on other materials in there. But here is a bit of a zoom in as we come in around the difference between 8.8 and 9.6. You can see here that corrosion rate keeps coming down, and most of the modern guidelines will recommend a feedwater pH around 9.8 these days for being the optimum point between the cost of adding something to increase that pH versus the pH where you get your best bang for your buck. So normally every plant you've got to adjust the pH of your feed water, unless you're going to build your entire feed water system out of, say, 316 stainless steel or something like that. But you'll find that the cost of building the plant out of a very highly corrosion-resistant material far exceeds the cost of spending a little bit of money on something like adding a bit of aqueous ammonia in to increase the pH. So how do we do pH control? Normally it's with a volatile amine, and aqueous ammonia is the most common. It's cheap, it's pretty easy to use. You just dose a little bit in with a dosing pump. If it's what we call a volatile amine, what it means is it dissolves into the water, but then it also goes into the steam, and it will then, when the steam condenses, it's still present in there. So what it will do is it will give you a pH correction in the feed water, then it will give you a pH correction in the condensate. If you can't use a volatile amine, so say you've got food contact with steam, where if there's any ammonia present in the steam, that impacts on your product quality, then you have to use what we call a solid alkali. We've got to use something that's not going to be volatile in the steam. And what we find is sodium hydroxide injected into the feed water is the most common solid alkali. So it'll give you a pH shift in the feed water, and then it will go into the boiler, and it stays in the boiler and doesn't transport into the steam. So and that's what you want. But again, depends on your plant, depends on whether you've got direct contact, if you've got non-contact heat exchangers, so that you have the process being heated on one side and the steam condensing on the other, then ammonia is normally your best choice because it works quite well. And it's easy, and there's a lot of science being done around its use. For dissolved gases, that's the next one. Normally people use a deaerator. Okay, and here we use Henry's law. So what we have is we have a vessel, and it's got the boiler feed water is sprayed in. We have some oxygen-free steam that's pushed into the bottom here. That flows up by Henry's law. We get gas exchange, and that steam strips the oxygen from the boiler feed water, and that'll be ejected out in the event. And then the water falls down. It's picked up some heat as well, and then it will remain in what we call the feed water storage tank, and that may have some steaming in there as well. And that's fine. Now, in the good old days, when we invented steam trains, the logic was that any oxygen is bad. So people went way out of their way with deaerators and dosing chemical oxygen scavengers to try to get the oxygen to zero, because it was thought that any oxygen is bad in any plant. Now, we've learnt a few mistakes around that, and we've discovered that some of that logic, if the plant is constructed out of all ferrous materials, it's all carbon steel, actually having zero oxygen is bad, and we actually want a little bit of oxygen present in the water. Because what we find is if we have pretty good quality water, okay, this graph's a little bit hard to understand, but here's our corrosion rate, here's our oxygen content, and these numbers here, 0.1, 7, 82, 850, these relate to the conductivity of the water in terms of its buildup of corrosive iron, so particularly chloride that's in the water. So the lower this conductivity, the cleaner the water is. And what we find is if we have pretty clean water, pretty good makeup water, if we actually have no oxygen, the corrosion rate is higher than if we have a little bit of oxygen present. You see the corrosion rate comes down. However, if we have contamination in our water, say we have chlorides get in via, you might have a seawater condenser or seawater cooling system, and then you get a bit of leakage in a heat exchanger and you get some process contamination. As that conductivity goes up with that corrosive material that's in there, as that oxygen increases, the corrosion rate increases. So oxygen is your friend and your enemy, but what we know is basically if we've got 5 to 10 ppb of oxygen, that's about optimum. We get actually quite good corrosion protection from that. Now what happens there is that if we have a little bit of oxygen present in the water, it helps with that protective oxide layer that wants to form. We end up with a little bit more hematite compared to magnetite, and that's a whole lot more protective. If you've got copper materials in your plant, then yes, you do have to dose an oxygen scavenger, and that oxygen scavenger is actually to protect the copper oxides that form on those copper materials. So if you're all ferrous, if you look at your material sheets and you say, I've got all carbon steel through my whole plant, or I'm stainless steel, and you have a deaerator, and you're dosing an oxygen scavenger, I'll give you some advice, which is you don't need to dose the oxygen scavenger, okay? And you actually want 5 to 10 ppb of oxygen, you don't want zero. So it's quite a common problem in industrial boilers because, you know, again, if I'm Mr. Chemical Vendor and I'm selling you an oxygen scavenger, they've got quite a good margin on them. They make quite a lot of money selling them, so you know there's a bit of a vested interest in continuing with that process, but you don't really need it. What the most common oxygen scavenger we see in industrial boilers is sodium sulfite. That gets added in, and again, this is directly derived from old steam train technology. And if you do this wrong, you basically get this risk of sulfate pitting, especially if you transport into your steam system, and that's probably one of the most common failures that we see in industrial boilers is sulfate pitting in the steam path, because they've been dosing sodium sulfite when they don't really need it, and it's coming through. Now, you may have heard about pitting and oxygen pitting. Yes, that is a corrosion mechanism that occurs, but what you need to understand is that actually only happens when the plant is shut down. Okay, it's a galvanic type process, and what it doesn't what it needs is like a no flow condition. It needs water sitting there stagnant and very, very high levels of oxygen, like approaching saturation, so sort of 9,000 ppb. So, you know, if you've got pits in your plant, and we'll talk about this in the next webinar, but if you're seeing pits that are growing, what it's telling me straight away is that you've got a layup and storage issue. Your plant is wet when it's shut down, and you've gone oxygen saturated, and you've got no flow, because oxygen pitting doesn't happen when the plant is in service. When you've got flow over the surfaces, you disrupt that galvanic process, and it doesn't occur. But yeah, that one's commonly misunderstood in the industry. So next one, boiler pH corrosion control. Okay, basically this curve still applies here. We want, you know, we want to be elevated alkaline pH in the boiler. Closer we get to 10, the better that it is. So how do we do that? Normally there's some, what we call a solid alkali is directly injected into the steam drum just to increase the pH a bit more if we need to. You can add that in via the feed water, but the control loop gets a little bit harder, but most boilers are all designed for the direct injection of an additional treatment chemical directly into the drum. It will have a distribution line that runs down, and you just need a higher pressure feed water pump. The most common products are sodium hydroxide or trisodium phosphate. Okay, and you want to avoid what we call mono or disodium phosphate blends. And if you get this wrong and you've got a higher pressure boiler, you can actually get a corrosion mechanism called acid phosphate corrosion, which can be completely avoided if your phosphate product is trisodium phosphate. And it's to do with the ratio of sodium to phosphate in terms of molar ratios, and it's a whole bunch of jiggery pokery that goes on when you get that wrong, and you can end up with causing a corrosion problem by incorrectly dosing the treatment chemical. But you're adding it in there for basically to elevate the pH to minimize that ferrous ion solubility, and also for scale control, which we'll come to next. Okay, so we want to make sure we're not getting scale forming inside the boiler on our heat transfer surfaces. So what we find is things like, you know, silica. The solubility of things like silica, as well as being changed by temperature, you can also, there's a pH influence. So if you've got a certain amount of silica present in your boiler, if we run at the right pH, we can minimize the risk of that silica starting to precipitate. If anyone's ever dealt with silica, once it precipitates, it's very difficult to remove from a surface because basically it forms a quartz-like deposit. And you've either got to mechanically remove it, you can't dissolve it off with most normal acids. You know, hydrochloric acid won't touch it, citric acid won't touch it. The only acid that will pick it up is hydrofluoric acid, which has particular health and safety handling considerations, and you really don't want to be, if you're not comfortable with hydrofluoric acid, you don't really want to be using it. But so you want to avoid silica precipitation if you can. The other thing that, in terms of scale control, one of the other things that we can do with phosphate is that if we're only using a water softener, you know, we will have still some calcium, magnesium type products that get through into the boiler. And if we add a bit of phosphate, we can form calcium, magnesium phosphates. And then these become insoluble, but they don't form a hard deposit. They'll form a sludge, and that can fall to the bottom of the boiler, and we can blow that out using a bottom drain. And that's the old way. That's the steam train way of doing it. You know, they used to take the river water from wherever, and you add the phosphate products in, and you complex it up, and you'd form these sludges, and then as you're driving along in your train, you open up the bottom drain, and you blow that stuff out onto the tracks, and that was how you cleaned your water out. The other way is by controlling the boiler cycles. So this is the water goes into the boiler, and as the steam forms, the steam is more pure than the boiler water, and these ions get left behind in the boiler water, and we call that cycling up. So one of the ways that we can minimize that scale is by controlling our cycles of concentration and increase the amount of blowdown. So we start to drain out a portion of that boiler water, and we replace it with fresh makeup water, so that we're trying to hold certain ions in certain concentration range. The other way is you can use sort of polymer type treatments. That some of these are specialty chemicals, and they operate similar to the phosphate. They form a soluble complex that stops the material from either precipitating or forming any kind of deposit, and then that can be removed via the boiler blowdown. But these are very specialized chemicals, and you've got to buy these from specialty chemical companies. So normally, if you're getting supplied by Nalco or Salinas or GE Water or someone like that, they would be offering these types of products. Well, the blowdown control is the next one here. So we know we're controlling blowdown to try to keep things in check in the boiler. And the most common way is there's a conductivity sensor which does a reading as total dissolved solids. It's just an approximate measurement. Proper total dissolved solids test involves a test in the lab. And what it does is that has a set point value that relates to how many cycles you want to run, which will be calculated based on what your makeup water is, the pressure of your boiler, and what your risk of ion scaling is. And then that sends a signal to a blowdown valve, and say that hits 100 and the set point is 99, then that blowdown valve will open a little bit and blow some of that out, and then takes that water out of the boiler, lowers the total dissolved solids in there because that water's been replaced by fresh makeup water, which has hopefully got a lower total dissolved solid. And this whole process is normally fully automatic. So like you might buy a unit like this from someone like Spirix Sarco or someone like that, and it's an all-in-one type unit. So you just got to make sure that the valves aren't getting blocked up and that TDS sensor is actually reading right and that control logic is set correctly. In terms of the next start, which is, we'll just talk about steam, so saturated and superheated and steam turbine, they're all basically linked. If you're getting deposition in one, you're getting deposition in all of them. So what we got to be concerned with is in the boiler we have a steam drum, and in that steam drum, which is at the top of our Foster Wheeler D type or any kind of boiler, and it's the same for, if you can imagine this as your fire tube boiler, you have water boiling. You've got a water layer and we've got wet steam being formed here. So here the water steam mixture comes in and it goes through a scrubber, cyclone scrubber, which separates the water from the steam, and then we have a secondary scrubber up here. And the idea of this is that saturated steam has as lower, entrapped moisture content as possible, because that steam is quite pure and that boiler water has dissolved ions in it. So if we are having what we call carryover, where the water droplets are getting carried through into the steam system, as you superheat that steam, then those ions that are in those water droplets will then form deposits very, very quickly. So the steam drum is a very critical thing for what we call a subcritical boiler. So two-stage separation, and we're trying to control carryover. So if you can imagine it, say the operator gets the drum level control wrong and that drum level comes up and it actually touches the scrubbers, and then we'll get water getting sucked through. Or if these haven't been attached properly into the boiler, or there's a hole or something like that, then you're going to get suboptimal steam chemistry coming out the other side. And what you need to do here is you should be doing periodic, what we call carryover tests. And if you go to that IAPS website, there's actually a test protocol available, and what you do is you measure sodium in the steam versus sodium in the boiler water, and you can calculate the ratio of carryover and determine whether you have a problem or not at your operating pressures. So it's pretty important, because if you get that wrong, okay, you get here's superheated tube, and it's obviously got a bit of a nasty white deposit, and this is a sodium sulfate predominant deposit here, because what was happening in this particular plant is their steam drum operating level was set too high during commissioning, and there was a very high level of background carryover where the water was being carried over, and that deposited onto those tubes, and then it resulted after 18 months operation in that superheated tube having such a heavy deposit that it overheated, and then it suffered what we call a creep failure here, and that resulted in the entire replacement of that superheater after 18 months operation. So wasn't a particularly good day in the office. Here's another plant, again very heavy deposits because of carryover in their superheater, and they have a small couple of megawatt steam turbine, and steam turbines are not meant to have these white deposits on the metal blades, and that's because it was sodium sulfate again transported through and carried through that particular plant. Came to me and said, hey, is it normal to have these big white crystals coming out of our superheater? And I had to say to them, no, there is none at all.
Okay, Dave, I'm just going to pause you for a second here. Have you got sort of some estimated sort of costs as a consequence for these sorts of things? So just you slide back the superheater, you know, and saying, okay, they got the chemistry wrong, you know, what sort of dollar consequence are you talking about there after only 8 months?
That particular one, the cost to replace that superheater was, I think, in the order of about 400,000 when you took into account the costs of the tubes, plus you have to cut the old one out and weld a new one in, and the downtime. So this isn't you know, a couple of days. This is a couple of week outage. Another one that I know of, which was after 9 years of operation, that was $1 million to replace the superheater. So these things can be pretty high cost that could be avoided by just some very simple and very low cost operational activities to make sure that A, your steam is the right purity and you don't have the carryover occurring. So cost of failure is often very, very high.
Yeah, so ballpark figure saying 800K to $1 million in terms of the failure repair bill versus the annual OPEX expense of getting it right to avoid it?
You're probably talking a few $1,000s.
Yeah, okay, yep. No, great.
Not much.
Yeah, just trying to put this into perspective for everyone. So no, great, thank you for that. So, you know, it's good to sort of recognise that yeah, it's not even an IRR calculation is what you're saying in terms of getting your procedures right.
Yeah, and the other one is if you've got even a small steam turbine, like steam turbine repairs are very expensive. You know, it's you don't even a 1 or 2 megawatt back pressure turbine. Often, if you've had a deposit that's resulted in some corrosion damage on that turbine, often they can't be repaired in New Zealand. They have to be shipped offshore back to the turbine OEM for remachining and blade replacements and things like that. So it's you've got the cost of repair, but then you've also got the lost opportunity cost because you might have been offsetting your electricity bill by running that turbine, or you may have actually been exporting to the grid and making a bit of money on the side as well. So that you want to avoid these types of problems if you can.
No, that's great. Thanks very much.
No worries. All right, so the other one that's a big problem in industrial plants is condensate purity, condensate return purity control, and this is a real major one because say you're producing steam for say an oil refinery, right, and you could get hydrocarbon return coming back. If you're a dairy factory site like Fonterra or some of the other ones, you can get milk products coming back. If you're a salt processing plant, you know, you may get brine or something like that, or basically it could be anything. So even if some of your steam is consumed in your process, you want to make sure that whatever's coming back in your condensate before you put it back into the boiler, that it's meeting specification is, you know, you want it to be. You don't want to be spending all this time and effort making good quality makeup water to find that your condensate is highly contaminated when it comes back. So, you know, it could be anything, milk, salts, hydrocarbons, could be your cooling water. And normally what you have to have is some means of contamination detected, normally online. So it might be that you have a conductivity meter and you know that if your condensate is clean, it'll have a conductivity of X, and any deviation above that is telling you that there's a problem. You might measure sodium, or you could measure silica. And normally what we find is most plants will normally have some kind of automatic condensate dumping system that picks up the problem and says, I'm going to dump that condensate. It's not good enough to come back to the boiler. It may go to a holding tank or be reprocessed somehow. Because often if you're waiting for the operator, they may not pick it up, and the damage can be done very, very quickly. So the other thing that may be required is you may have to have what they call a condensate polisher, which is as the condensate comes back to the plant, to the cogen plant or the boiler house, it goes through an additional water treatment step to remove any process contamination that may have been picked up as it goes through. So, you know, the big power plants like Huntley units, they all had condensate polishers, and that was to protect in case primary heat exchangers had a leak and we had Waikato River water getting into the boiler feed water, so we could protect the boilers from that. And these systems often look like this. You've got your condensate return coming through here. There's a conductivity sensor or some sensor of some type on a bypass line here that's got a flow going to drain. It's got a controller, and you've got a valve here that's either letting the condensate go through, or that valve changes position and it will dump that contaminated condensate to waste. Now, often a lot of plants will have some system where you can perhaps do 100% condensate dumping for a few hours, because then you start to run out of water because you're exceeding the makeup capacity of your water treatment plant. And normally that's enough to, say, identify where in your plant the process contaminant, there might be a heat exchanger or something's gone wrong. It's to buy you time to go and fix the problem or isolate that part of the plant and then get that condensate coming back, or that clean condensate coming back to keep the plant going. So pretty common to have a condensate return dump type system. All right, so the next one, sampling and analysis. You know, basically you can't control what you can't measure, and you know, I'm a big advocate of this, is that automatic online systems are preferred over manual grab sampling systems, but we do acknowledge that cost and complexity is potentially very high for small plants. The problem is you have a big 1,000 megawatt boiler, you've got to put some online instruments on it. The cost is exactly the same for a 1 megawatt boiler. There's no really economy of scale here. So I call this the curse of cogen, where you have all the problems of the big plants, but your budgets are a lot smaller. So you got to be pragmatic and say, what do you absolutely need? Is it going to generate me some value? Is it going to protect me from a very high cost type problem, or is it just a nice to have? So what we normally find for industrial boilers, that there is no online sampling analysis systems except for maybe boiler blowdown control, or maybe some kind of condensate dump or condensate dumping system. But what I can point you to is, you know, there's an IAPS guideline for instrumentation that you can kind of use as your starting point to say, here's what we recommend for the big plants, and there's also layers of redundancy built into that. Can I kind of pick and mix out of here as something what's going to give me my best bang for my buck? And you can go from there. So just looking at these slides here, you know, condensate pump discharge would be equivalent to condensate return, and we could be measuring conductivity after cation exchange, which is a means of detecting contamination. Could be measuring dissolved oxygen, or could be measuring sodium. And decase is degassed conductivity after cation exchange. You know, and you might say, look, out of all of those, you know, sodium is my biggest risk. That tells me a whole bunch of information about if I've got a process upset. Maybe I'll just put that in there. You know, and we go through this list as a whole. I'm not going to go through it in detail, but it gives you some guidance around what you could do, and then, you know, you go through a risk-based, cost-based, you know, what's practical and possible, and weigh that up against, you know, if I take a sample once a day, the operator does a grab sample and does a test, is that going to provide me adequate warning of a major process upset or a major plant upset? The problem that we find is that often if people are doing, you know, one test a shift, and you say to them, you take that test, and if it's out of spec, what do you do? And normally they go, oh, well, I assume that the test was wrong, so I do it again tomorrow. And if it's the same tomorrow, then I assume there's something wrong then, and you're going like, that's great, now you've been out of control for perhaps 2 days. Okay, where if you had an online instrument and you could see a trend, you could see that it's starting to trend up, and it's been like that for a little while, so you need to do something about it right away. So there's pros and cons to online and offline analysis. So again, there's a whole lot of stuff in those IAPS technical guidance documents. So if you're thinking about, have you got the right instrumentation from your plant, I'd encourage you to get the free download, have a bit of a read and a think, and then, you know, ask around, and you might be able to get some advice on what you need for your plant. All right, so
sorry, Dave, I'm going to just pause you there for a second. Obviously a key topic, and hopefully people will go and read, but for those that are just looking for the helicopter view today, in all your experience, is there one or two critical things for a typical industrial process heat boiler that you'd summarize and say, hey, look, these are the things that you should really look at? So say, for example, someone's seen the presentation today, grabs a few of the slides to scare the bejeebies out of their boss, to say, hey, look, holy cow, we can't afford this sort of expense. And so maybe they can get a little bit of money out of the stone. You know, there's only so much blood in the stone. So, you know, could you give any real, I appreciate it's sort of all care and no responsibility because it's very specific to each application, but in general terms, if you have some real simple, basic, hey, really good pointers where to get started as a take home for everyone.
Well, first and foremost, you need something on your condensate return for if it's interacting with the process. So, and if you've got a heat exchanger where the steam or the condensate is at a lower pressure than the process, so if you could leak back, and that's milk or hydrocarbon or seawater or something like that, then you need some kind of condensate return contamination detection, and conductivity meter would probably be the simplest and most basic one there. If you have a superheater on your plant, at a bare minimum, you need a sample point which has a sample cooler so that you can at least get a grab sample to do the carryover test. And we've seen a few plants built in New Zealand where have superheaters, but they never actually had a sample point installed. Okay, so that they couldn't even do a carryover test if they wanted to. You know, and that's resulted in all kinds of problems. And the boiler itself, obviously, if you got automatic blowdown control, there'll be a conductivity or a TDS controller in there. I would recommend pH on the boiler as well. So, but for pH, you've got to have a sample point which has a sample cooler to bring the temperature down. If you've got a deaerator, you know, having a dissolved oxygen analyzer on the outlet of that as well is quite useful, and often a pH meter on your feedwater. So again, if you're dosing ammonia or you're trying to get that pH 9.8 to 10 in your feedwater, actually being able to verify that with a pH meter is very helpful. And then it also means that you can set up automatic control loops where you have a pump controlling to a set point, which lowers your manual operator intervention and things like that. And that would probably be my minimum recommendation there. Okay. All right, so the last one here on the list, and hopefully we're going to be on time, is layup and storage. So say you got everything absolutely perfect with your, and we find this actually out there in the world, people have all their operating chemistry pretty spot on, and they run their plants really well, but when they shut them down, everything corrodes and they have all their problems start from the offline environment. And this is quite pertinent to, especially Fonterra plants or plants that have a seasonal operational type mode where they might be shut down for a few months. So what we get is boiler standby corrosion, where we get unwanted formation of non-protective iron oxides, which is rust. So here we have a boiler, it's a heat recovery steam generator steam drum in Australia. It's been shut down for an outage and they didn't get all the water out. And you can see here, here's a puddle of water sitting here in the vessel. And straight away you can see it's rusting away, and it's actually pitting away under there because that water is now 100% oxygen saturated. And over time, the pH goes down and away you go. And this is me doing a boiler inspection, and we're marking out things that we're finding in there for the plant owner, taking photos and going back to them and telling them that it's not right. And basically, if you've got an environment which is you've got higher than 30% relative humidity, then you're going to have offline corrosion. And it's often ignored and neglected because people just shut their plants down and just turn it off and say, all right, we're not running it for a month, we'll just walk away. And if you're in reserve, or you're the backup boiler, or you're starting and shutting down a lot, this is really where you get a lot of problems. And it's absolutely critical for steam turbines as well, especially if you've got seasonal operation on a little steam turbine, and it might sit there the rest of the time. So we see problems like this, and you can see here where there was a puddle of water and it's caused some corrosion, and then it's finally all evaporated away. But what happens is when that plant starts up, that oxide is non-protective and it just washes off, and then it transports through and will cause some problems elsewhere in the plant. So what are we interested in here is, here's a thing called the Vernon curve. It's from Mr. Vernon back in 1935, and this explains why things rust in the jungle and don't in the desert. So corrosion rate here, humidity there, this is for carbon steel, we're 100% humidity. Under oxygen saturated conditions, we have very high corrosion rates. As we get drier and drier and drier, basically when we get down to less than 30%, the corrosion rate goes to 0. So if you've got a boiler and you say, I don't need to run it for 6 months, or I'm shutting it down, we would recommend that you blow it down hot, you get all that water out, and then you either use something like instrument air, or you get a turbine, or you get a dehumidification system in there, and you dry it out, and you try and get the internal environment of all the water touch surfaces down below 30% relative humidity. And basically you can say that the boiler is now in suspended animation, and there should be no corrosion occurring. Okay, and a dehumidifier is normally Munters dryers, but this is what they look like on the inside. You have a self-regenerating desiccant wheel. Okay, so we're bringing in, humid air comes in, gets dried through that desiccant, comes out, goes into the process, and then there's this desiccant wheel turns. It's got an air heater. It's driving the moisture out of the desiccant, which is being ejected, and then it's being continuously regenerated and continues to be dry. And a properly sized unit will produce 5% relative humidity, and it's one of these things that you hook it up to your boiler. You drain the boiler down, you hook this up, and you're putting 5% relative humidity at one end, and you blow it through the boiler. You have a flow path set up, and you measure the humidity coming out the other end. And if that might be like 60% on day one, and you blow that air through, and it might be 30% on day two, and then it might be 2% on day three, and then you can put your hand on your heart and say, the boiler's now dry and it's in a protected state. So this is really a lot of problems I see around the world is due to poor layup and storage, where people have initiated a whole bunch of corrosion problems because of the way they've stored the plant. And things like if you get pits in certain locations, the pit, eventually it'll cause a through-wall failure on its own, and that's a problem. But the problem is you've created an irregularity in the surface, and there's a whole secondary bunch of corrosion problems that occur because you get cracks that then form from the pit when you put the plant in service. When you come up to temperature and pressure, there's stresses applied to the plant. You can get these things called stress corrosion, cracking, and corrosion fatigue, particularly in turbines and superheaters and heat exchangers that have got some kind of tensile stress present on them. So something you need to watch out for. All right, and so we've pretty much got to the end, and I know this has been a bit of a roller coaster ride, and we're going to do some more on the corrosion mechanisms in the next one. But basically, in summary, the cycle chemistry goal was to minimize corrosion and deposition, and it's a very complex area of science. And note, I don't say eliminate, because we can never quite fully eliminate it, so we always try and control it and bring it to a minimum. There's a lot of misinformation and confusion out there, and I blame the steam train for that, but also some of that comes into what's right for one design and pressure of boiler is not necessarily right for another. So you've got to understand the cycle. And I recommend use a guideline, best practice, current, take a free one from IAPS, or you can look at purchasing the ASME one and things like that. And you need to consider the whole cycle. By doing one thing in one location, are you creating another problem further down the path? You might say, hey, I'm going to dose ammonia because I heard that's really good for my feed water, and that goes off and you realize you've now contaminated your very expensive product that you're making, and now you can't export that. So you've got to, any changes to your chemistry, especially for any plant that's producing food or pharmaceuticals or something like that, you need to go through that risk type analysis process, do a HAZOP and say, am I creating a bigger problem by doing this, or is there a better way, and things like that. So there's some additional information. I pointed this one out, the IAPS technical guidance document. There is actually a journal for power plant chemistry, which covers a lot of stuff around industrial boilers. So, that's, you go to ppchem.net, you can pick up an electronic subscription, and they have a few papers and things like that available. You can drop me a line as well, and I can probably send you a few bits and pieces. And then, does James want to do the last bit here for what's coming up next?
Okay, so thanks very much, Dave. Now, just before I get into this, just a quick note. So that sort of concludes Dave's presentation today, and on behalf of everyone, thanks very much, Dave. It was very informative. And obviously, if you've got any issues, feel free to, or questions, you can email them through. We will stay on the line for a few minutes now. If anyone wants to fire through questions through the question portal, you can just punch in your question, and if you're mic'd up, we'll try and get you online. Otherwise, we'll try and address your question either way. And just as any of you might be thinking about putting a question in, just a reminder here that we've got some webinars coming up. I do apologise, there seems to be a bit of confusion, but the next webinar actually in 2 weeks' time is going to be on VSDs. It's with myself. The week of the 30th of March, we're actually having a break around the Easter holiday period, just in recognition there's lots of people going to and fro, a bit of time off, etc. So there won't be a webinar the week of the 30th. So the following webinar will be the April the 6th on refrigeration process cooling. And then April 20th on mass and energy mapping for process heat systems. So getting into the meat and in terms of how we need to address getting optimization in our process heating and cooling systems. So yeah, so on that note, really, I guess that's the webinar's coming up, and there's been a couple of people commenting today are asking questions, and just to reaffirm that the presentation today, the audio and slides will be available as per the YouTube channel that EECA has set up that can be accessed from their website. Now for those that can't access YouTube, EECA has set up a Dropbox. We're just sort of working through the finer details of that, but if you're looking for that information, you can email me at jamesn@waikato.ac.nz for more details if you need that. So yeah, so just a reminder, yes, the slides are available along with the slides and presentations from the previous webinars for review for yourselves, or to be able to share with your team or your boss to say, hey, look, we need to look at this. You know, you might just be able to go to a certain part and you can show that. So yeah, so on that note, we're happy to carry on. We've just had a question, Dave, that's come through from Pramesh. How common is online dissolved oxygen monitoring and blowdown control in the industry? You mentioned it's obviously useful.
Automatic blowdown control is extremely common. In fact, I'm struggling to think of any industrial boilers I've seen in the last few years that didn't have an automatic TDS type controller on them. Normally, the reason for that is that when you buy an automatic blowdown valve, like say a Spirix Sarco type unit, it comes with the conductivity unit built into it, right? It's like that's the module, and most of them are supplied by RCR and things like that. Dissolved oxygen is less common, but it is still pretty common, either via a permanently installed online meter, or some sites might say have multiple boilers, they'll purchase a portable unit that can be connected up for deaerator testing. Often you find that if you're using a chemical vendor to provide your boiler chemistry services, they will have them as well. And if you ask for some dissolved oxygen testing to be carried out, I know Nalco and GE and things like that have the equipment and they can come and do it. All you got to do is just connect up to like a 3/4 inch swage lock port, and you can run the instrument and away you go. I actually have one myself as well for doing R&D work and investigation work at client sites, and they're maybe $6,000–7,000 New Zealand for a portable unit, but less for a permanently installed one, and they work quite nicely.
All right.
So yeah, hopefully that answers that question.
Pramesh, are you mic'd up? No? No, excellent. All right, no, thank you, Pramesh. So we'll hang around for a minute or two more if anyone else has got a question, but otherwise, if there's no more questions, they feel free to carry on with your day. And just a reminder that the slides and everything will be available, and stay tuned for the invite that will be sent out for the webinars coming up in the future. Okay. Okay. Hey, thanks very much to everyone who's passing on their appreciation. But on that note, in the absence of any more questions, we'll tidy up today. And if you still have questions that come to you, by all means, feel free to send them through by email, and we'll do our best to assist where we can. So thank you very much, and we'll see you all in 2 weeks.